Hi everybody, this is Sylvester Stallone and this is board problem 49 and we're going to talk about confidence intervals next. The average noise level in a cafeteria is 36 decibels with a standard deviation of 5. Assuming it's normal, what's the probability that a noise level is between 30 and 40 decibels? Well, we've learned how to calculate them by hand, you guys, but here's a shortcut on doing it on the calculator. If you go into this is a confidence level or confidence interval calculation, you guys, sorry. And if you go into your graphing calculator, this does this for you. It's under distribution, which is in your second function variables button, and then choose normal CDF and plug in normal CDF and then 30 for the 30 for your bounded by your confidence interval, 30 comma 40, and then 36 would be the mean, and then 5 is the standard deviation, and if you enter that you get 0.673. So try that and be aware of where that is, because we're going to start doing almost everything on a calculator now, so be aware of that. Okay, so it's kind of a long lesson, you guys. It's not hard, it's just a lot of writing. Hooray, smile with me. I know you're laughing right now. Lots of writing. Sorry, you guys. Confidence interval for a population mean. So finding, this is called the Z-score. So that little, or the Z-star. Sorry, you guys. So we're going to find the 80% confidence interval. And so when we find the 80% confidence interval, that means there's 20% left out, obviously, right? And so there'd be 10% on each side. I hope that makes sense. So this would be my 80% confidence interval, and so 10% gives me the 100%. I know that makes sense to you guys. So the Z star is the point at which point 1 is to the right, or even better, since our table always gives to the left. Okay, here's point 1 right here. Isn't that right? Because it's 100% over from here down below. So this is, since that's 10%, this is the 0.90th percentile, and since it gives me to the left, I go down to the left. There should be a space right there. Sorry. Oh, let's just fix that right now. Sorry. There we go. All right. And then, so let's put that back in there. So search the body of table A and find the Z-score that gives you closest to 0.9. And so if you find it, you'll find the closest one is, so locate that in table A in the front of your book. 1.28 is the one that gives me the closest to 0.9. All right, so there's an area of 0.8 under the standard normal curve between z equals negative 1.28, because this would be the 1.28 right here. So over here would be the negative 1.28, and this would be 80% of the curve right there. All right. So your graphing calculator does this part under distribution, you guys. So if you do inverse normal distribution, that's what norm stands for, and plug in 0.9 on there, you guys, and you enter and you get 1.28155, so like 1.282. All right. So graphing calculator does, I just copied that so you can see that in case something was in the way down there. So to find the confidence level, in the prior example, see, our confidence level was 80%. So each tail is 1 minus c divided by 2. So 1 minus 80% is 20% divided by 2. Each tail gave me 10% on each side. That's all that says right there. So here's the results for the most common confidence levels in C. Okay, so we're going to make a few columns right here. So the confidence level, so the confidence level of 80%, 85%, 90, 95, and 99%. Those are the most common ones we're going to use. Okay, and so if the 80% we just calculated is 10%, because we did 1 minus 80 divided by 2, and the z-score was 1.282. That's what we got in our calculator. So 1 minus 85 divided by 2. Oh, you can do inverse norm on that, sorry. Also, inverse norm of 0.9 gets me that right here. All right, so 1 minus 85 is 15%, and divided by 2 is 7.5%, so each tail is 0.075 right there. Okay, so if we did inverse norm of 0.075 in our calculator, we'd get, or not 0.075, 0.925, because it's always to the left, you guys. I'm sorry, you guys, it's always to the left. Okay, does that make sense? Because this is 7.5% down from 100% right there. Okay, so for the 90%, 90 divided by, or 1 minus 90 is 10, divided by 2 is 5%. So we're going to do inverse norm of the complement of that. So you get all of these right here. Okay, these will be popping up a lot. You don't have to memorize these. These are always given to us in one place or another. In fact, they're in table C in the back of cover of most of your books. For some reason, some of your books does not give table C. So if it doesn't, I'll see if I can copy some off and give them to you when we return. Okay. Gives you the z-scores for all of these. So here's some critical values. Otherwise, you have them in your notes right there, okay, if you don't have them on table C in the back of your book. Okay, so the number z star with the probability p lying to its right under the standard normal curve is called the upper p critical value of the standard normal curve. So that would be the probability of p right there. Okay, and so the confidence interval for a population mean, so you choose an SRS of size n from a population having an unknown mu and known standard deviation sigma. A level C of confidence interval for mu is, here's our formula. We're going to make this our friend, you guys. We're going to use that so much you're going to get, it's probably going to become memorized in you. So your confidence interval is going to be your sample mean plus or minus your z-score. Okay, so what we just calculated, the standard deviation divided by the square root of n. Okay, so we're going to go ahead and, so your z star is the value at which C is between negative z and positive z under the standard normal curve. The interval is exact when the population is normal and approximately correct for the large n and other cases. Okay, so conditions to be able to construct a confidence interval for population mean. So if you can't do any one of these don't satisfy, then you're done. You can't do it. So the data comes from an SRS that's from the population of interest. So I can't calculate grades and then go out and calculate the water height in Sacramento River. That doesn't come from the population. Okay, it has to come from the population. And the sampling distribution has to be approximately normal. If that case happens, then you can do the next procedure. So here's video screen tensions, example 10.5 on page 546. Sorry about the light picture colors. The book is not picking it up very much in this chapter. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow it for wrinkles. The tension is measured by an electrical device with output readings in millivolts, MV. Some variations is inherent in the production process. Careful study shows that when the process is operated properly, the standard deviation of the tension reading is 43 millivolts. We'll use that 43 in a little bit. And here are the tension readings from an SRS of 20 screens from a single day's production. Okay, so here's an SRS, 20 of them right there. Okay, when you get some time, let's do it right now. Plug those in list 1. Pause it right now and plug those in list 1. You'll see why later. All right. All right, so we're going to construct a 90% confidence interval for the mean tension. So we're going to use that formula that was in the box for the mean tension of all screens produced that day. Okay, so it's step 1. You have to write these down. Sorry, this is that we're going to do this on all your problems. You have to do this. Sorry. Identify the population of interest and the parameter you want to draw a conclusion about. Okay, so our population of interest is all video terminals produced on the day in question. Here goes an announcement. We want to estimate the mute. You guys want to listen to this? Let's listen to this. Okay, sorry. So we want to estimate the population mean of the mean tension for all of these screens. Okay. Step 2. Got to write it down. Sorry. Choose the appropriate inference procedure. Verify the conditions for using the selected procedure. And since we know the standard deviation, we should use a confidence interval for a population mean that we just introduced. So that formula right there to estimate our mu. Okay, and now we must check to see that the requirements are met from section E. Okay, so the data comes from an SRS of 20 screens. From the population produced, so it's an SRS of our population of interest, so we're good there. And then, so is the sample normal? Well, from past experience, we say yes, but what we ought to do is examine the data. So we're going to do a stem plot over here. So here's a stem plot right here, okay? So check out that stem plot and kind of look at it sideways, tilt your head to the right like I'm doing right now, and see how it's kind of a nice bell-shaped curve right there? Okay, the stem plot shows no clear outliers or strong skewness, so it looks pretty good. So it looks pretty normal. So we can go on to step 3. Yes, write this down. If the conditions are met, carry out the inference procedure. Okay, here's our formula. So calculate the mean. So do a one variable statistics with list 1, you guys. Okay, you have that in your calculator, and you should get your sample mean to be 306.3. So pause it right here and make sure you do that. All right. Okay, and then. So for 95 or 90% confidence interval, our Z star was from the beginning of the notes is 1.645 from section B of our notes. Okay, and then so here we go. So we're going to just plug it in. It's just number crunching now. And here's the standard deviation, that 43 divided by the square root of 20. And when I plug it in, I like to do this first, you guys. I like to do 43 divided by the square root of 20. Find that value out, multiply that times 1.645, and then put that number aside. Whatever that decimal is, then I add 306 plus that decimal and then 306 minus that decimal. And then here's the interval. It says 290.5. My confidence interval is between 290.5 and 322.1. Okay, your book is going to write it like this. Okay, that just says it starts at it's greater than 290.5 and less than 322.1. All right, and then step 4 is to interpret the results. All right, so we are 90% confident that the true mean tension in the entire batch of video terminals produced that day is somewhere between 290.5 and 322.1 millivolts. All right, yes, you have to do that. Okay, so let's look at figure 10.8 at the bottom right here. Here it is right here. And what this says is when we had a sample size of 1, it gave us a very large confidence interval. This is the confidence interval for a sample size of 1. When we did a sample size of 2, we calculated it to be this interval right here. And so larger samples give shorter confidence intervals. That makes sense. Okay, real quick. Okay, sorry, it's easier just to copy this out of here instead of trying to do this, but yes, I want you to write this down. The estimate plus or minus your z-star times the standard deviation of your estimate is your confidence intervals estimation, where the estimate is the center, okay, and so this guy is the center, so usually your x-bar, and the margin of error, which is MOE, we'll talk about more later, is this stuff right here. Alrighty, and so the estimate, whoops, that should be an x-bar right there, an x-bar from an SRS, and standard deviation is the estimate is your x-bar from your SRS, sorry, and your standard deviation is this old formula that we've used before. Alrighty, I'm just going to go ahead. Here's your homework right there, page 548 and 49, 10.5 to 10.7 all.